We're on problem, where are we? 145. Problem 145 says, is 1 over p greater than r over r squared plus 2? That's their question. Statement number 1. I realize I go on these tangents before even looking at the statement. I should look at the statements first. P is equal to r. So let's see if we can simplify this. So this if p is equal to r, then we get 1 over r instead of a p, right? Is greater than r over r squared plus 2. Let's multiply both sides of this equation by r. So then we know that, well, we don't know that r is necessarily greater than 0. That's the problem. We don't know, because without knowing that r is greater than, so if r is greater than 0, well, it's going to change the inequality one way or the other. So if r, let's just assume r is greater than 0. So if we multiply both sides of this equation by r, then we don't have to switch the inequality because we're assuming r is greater than 0. And that's an assumption. Then you get 1 is greater than r squared over r squared plus 2. And then if r is greater than 0, then r squared plus 2, actually, r squared plus 2 is always going to be greater than 0 because r squared is going to be positive. Let's multiply both sides of this equation by r squared plus 2. And you get r squared plus 2 is greater than r squared. You can subtract r squared from both sides, and you get 2 is greater than 0, which is true. But remember, I had to make this assumption that r is greater than 0. If you assume that r is less than 0, then all of this is going to break down because you're going to get, because when you multiply both sides by r, you have to switch the inequality, and you get 1 is less than r squared over r squared plus 2. And then you'll end up with, well, eventually you're going to end up with r squared plus 2 is less than r squared, or that 2 is less than 0, which is false. Right? So this statement alone isn't enough. We have to know whether or not r is greater than 0. Statement 2, well, there you go. R is, I really should look at both statements first. R is greater than 0. So, and just so you know, statement 2 by itself isn't sufficient, because if you know that r is greater than 0, you have no idea of what p is, so you can't answer it yet. But both statements combined are sufficient to answer this question. Next question. 146. Is n an integer? N an integer. Is n an integer? Statement 1 says n squared is an integer. N squared, an integer. Well, that doesn't help us. I mean, you know, what if n was equal to the square root of 2? And then n squared would be equal to 2, which is an integer. But this is clearly not an integer. But on the other hand, n could be equal to 2, in which case n squared would be an integer. So whether or not n squared is an integer, both of these are cases where n squared are an integer, but one ends up where n is an integer, one is where n isn't an integer. So this by itself is not enough to tell me whether n is an integer. Statement 2 tells us. Statement 2 tells us square root of n is an integer. Okay, so that essentially tells us that n is equal to some integer squared, right? I mean, you could take the square root of both sides and you get the square root of n is equal to some integer. So you take any integer, you square it, you're going to get an integer. So statement 2 alone is sufficient to answer this question. That was a strangely easy question. They were getting a little bit hairy and confusing, but that was a nice little rest question, I think. 147. 147. If n is a positive integer, so n is a positive integer, well, n is greater than 0, it's an integer as well, I didn't write that down, is n to the third minus n to the third minus n divisible by 4. Fascinating. Fascinating. Let's see. So, I don't know, my initial reaction is to see if I can simplify this as the product of simpler expressions, because I don't want to take, I look already at statement number 1. Let me look at statement number 1. Statement number 1 says n is equal to 2k plus 1, where k is an integer. I don't feel like taking 2k plus 1 and cubing it. That's not an easy thing to do. It'll take some time. So my intuition is that maybe we should simplify this a little bit. So if we factor out an n, that's equal to n times n squared minus 1. And that's equal to n times, what's n squared minus 1? That's n plus 1 times n minus 1. And now this is something that's much easier to substitute this into. So let's do that. Let's substitute n equals 2k plus 1 into this. So if n is equal to 2k plus 1, you get 2k plus 1 times 2k plus 1 plus 1. So that's 2k plus 2. That's this one. And then you have 2k plus 1 minus 1. So that's just 2k. And then what does that simplify to? You get 2k plus 1. Remember, in the back of my mind, I want a 4 to show up because I want this thing to be divisible by 4. 2k plus 1 times 4k squared plus 4k. Interesting. So now I can factor out a 4, right? So it's 2k plus 1 times k squared plus k times 4. And we know that each of these, that this is an integer, right? Because they told us that k is an integer, where k is an integer. We know that this is an integer, because k is an integer. And we know 4 is an integer. So we've essentially kind of factored n cubed minus n, and 4 is one of its factors. So it's definitely divisible by 4. I mean, we can divide it by 4 right now. If we divide it by 4, we'd be left with this, which is clearly an integer, right? Because k is an integer. So n to the third minus n is divisible by 4 if we can assume that n is equal to 2k plus 1, where k is some integer. Now what do they tell us in statement 2? Statement 2. Statement 2 tells us n squared plus n is divisible by 6. Well, I don't see how that's helpful at all. I don't even. N squared plus n is divisible by 6. I mean, you can't even relate to that. I mean, n squared, and I could try to do something fancy no, but this is just, this is so different than this. N squared plus n is so different from n to the third. There's no, I could factor out an n. I could say n times n plus 1 is divisible by 6. Well, I guess that's interesting. That tells us that this part is divisible by 6. N times n plus 1 is divisible by 6. That tells us, that, do they tell us that n is a positive integer? Yeah, they do tell us that n is a positive integer. So this could be 2 and 3, right? If this is 2 and 3, then this would be 1. Right? This could be 2 and 3. In fact, this could be 2 and 3, but it could also be, actually that's the only numbers it could be. It could be 2 and 3, in which case this is 1, in which case this whole thing, right? N could be, if you say this, then n could be 2, n is equal to 2, n is equal to 2, n plus 1 is equal to 3. N plus 1 is equal to 3, and then n minus 1 would be equal to 1. And so this whole expression, and let me see, is that the only case? I'm looking at the answer right now just because I want to make sure. They say that this isn't sufficient, but once again, kind of like problem 142, because if you say that n is a positive integer, and that n times n plus 1 is divisible by 6, I can't think of any other numbers where you multiply one number times the next number, and they're integers, where you get a multiple of 6. Oh, well, no, I take that back. It could be 3 and 4, right? There could be 3 and 4. It could be, there's actually a bunch of them. So it could also be, this could be 3, this could be 4 because it's a multiple of 6, and then this would be 2. So that's right. This is not enough information. So that's good, because by this information, n could be 2, n plus 1 could be 3, in which case this number would be actually 6. But that still doesn't help us because 6 isn't divisible by 4. But then I could come up with a situation where this number right here, where n is 3, n plus 1 is 4, and n minus 1 is 2, where this does become divisible by 4. So this doesn't give us enough information. Not useful. And I'm out of time. I'll see you in the next video.